Today we will talk about dynamic analysis of structures. We will explain the difference between static and dynamic analysis, and we will show why the dynamic analysis is important. We will explain the meaning of some common terms used in dynamic analysis, such as single and multiple degrees of freedom, mode shapes, and natural frequencies. We will briefly explain the main methods used in the dynamic analysis of structures, the time history, and the model analysis. The main purpose of this lecture is to introduce the topic of dynamic analysis. God willing, in future lectures, the topics introduced today will be discussed in more details. Let us first explain what is meant by a dynamic analysis. For the shown cantilever with the mass on the top, if we instantaneously applied a 10 kN force on the mass, the cantilever will deflect and will generate internal forces. When the mass reaches point B, the internal forces generated in the cantilever will be in equilibrium with the external 10 kN force, and in theory, the cantilever should stop moving. However, due to the sudden application of the force, the velocity will not be zero when the mass reaches point B, and the mass will move further until it reaches point C. The additional internal forces generated due to the additional deflection from point B to point C will decrease the velocity of the mass until it becomes zero at point C, and it stops. At point C, the internal forces will be larger than the external applied force, and this will cause the mass to move back towards point B. Again, when the mass reaches B, its velocity will not be zero, and this will cause the mass to move further until it stops at point D. At point D, the applied force will be larger than the internal force, and this will cause the mass to move back towards point B. This oscillatory motion will continue around point B until the motion is damped out and the point stops at the static equilibrium position at point B. The internal forces generated in the cantilever at point B represents the long-term static effect that is generated in the structure. The additional value of the internal forces due to the increase of deflection from point B to point C represents the temporary dynamic effect due to the sudden application of the force. If the force is suddenly removed, then the cantilever will vibrate in a free vibration around point A until the motion is damped out and the cantilever is stopped at the undeflected position at point A. So, when is it important to consider performing a dynamic analysis? From the preceding example, it is clear that the dynamic effect is a temporary effect that is caused by sudden variation in load. Dynamic effects become important in cases where there is a sudden change in the loads, such as impact loads and earthquakes, or when the load is continuously changing, such as structures supporting vibrating machines and due to the effect of moving cars on bridges. Dynamic forces will have two possible adverse effects on structures. Number one, the internal forces generated due to the sudden dynamic force are larger than that generated statically. In some cases, the dynamic internal forces are more than twice the static forces. Number two, the vibrating forces that are continuously acting on the structure can cause fatigue failures. How is dynamic analysis of structures different from the static analysis? In a static analysis, the equilibrium equations include the external applied forces and the internal forces generated in the structure due to the deflection. When the sum of these forces becomes zero, equilibrium is attained. In a dynamic analysis, the equilibrium equations will include inertia forces in addition to the external and internal forces which was included in the static analysis. The inertia force is equal to the mass multiplied by the acceleration. Before going deeper into the topic of dynamic analysis, we need to explain the definition of some terms that are widely used in the dynamic analysis books. First, we will explain what is a shear frame. The shear frame is a special type of frame used to simplify the dynamic behavior of single-story and multi-story shear buildings, such as buildings that depend on shear walls to resist lateral loads. This frame is rigid in the vertical direction and doesn't allow any deflection or rotation within the span. It is only permitted to sway in the horizontal direction. Next, we will discuss what is the difference between a single degree of freedom and a multiple degree of freedom system. A single degree of freedom has only one independent degree of freedom, such as the shown one-story shear frame. The dynamic analysis of this frame is quite simple because it only has one unknown movement. The multi-degree of freedom system has more than one independent movement, such as the three-story shear frame shown, which has three independent movements or 3 degrees of freedom, a degree of freedom at each story. The dynamic analysis of multiple degree of freedom structures is more complicated. Let us first study the free vibration of a single degree of freedom structure. When a horizontal force is applied on the shown one-story shear frame, the frame will sway in the horizontal direction. If the force is suddenly removed, the frame will start to vibrate in a free mode back and forth around its undeflected position. The time needed for the frame to complete one cycle of vibration is called the natural period of vibration, and the number of cycles that the frame completes in 1 second is called the natural frequency. One important feature of this free vibration is that the natural period and the natural frequency are always constant for the frame, and doesn't depend on the magnitude of the force that initiated the vibration. It only depends on the mass and stiffness of the frame. For a multi-degree of freedom system, the analysis of the free vibration is not as simple as a single degree of freedom system. For the 3 stories shear frame, we will find out that the frame has 3 natural frequencies or 3 natural time periods and not one as the single-story frame. We will also find out that each natural frequency is associated with a specific shape of vibration called a mode shape. If the frame vibrates with the first natural frequency, the shape of vibration will always be identical to the first mode shape. If the frame vibrates with the second natural frequency, the shape of the vibration will be the second mode shape. And if it vibrates with the third natural frequency, the shape of vibration will be the third mode shape. The free vibration of the multi-degree of freedom frame will be identical to one of the 3 natural modes of vibration or a combination of the 3 modes. If the 3 stories shear frame is subjected to a system of forces, and then the forces are suddenly released, the free vibration of the frame will be a combination of the 3 natural modes of vibration. The ratio of each mode in the free vibration motion will depend on the force configuration that initiated the free vibration. So how do we perform dynamic analysis? For single degree of freedom systems, dynamic analysis can be performed using the time history method or using the analytical methods found in dynamic books. Dynamic analysis of multiple degree of freedom system can be performed using the time history method or using model analysis. Details about each of these methods will be given next. For the analytical methods of dynamic analysis, the solution is a closed-form mathematical equation, and therefore it is a very fast method. However, the solution depends on the type of loading. Fortunately, closed-form solutions for several loading conditions on single degree of freedom systems are available in dynamic books. Also, this method is limited in application. It cannot be used for all loading conditions, such as random dynamic load, and cannot be used for nonlinear analysis. To perform a time history analysis, we need first to choose a suitable time step, which should be a fraction of the natural period of the structure, maybe 5 to 10% of the time period. We start at time 0 when the structure is still at rest. The displacement, velocity, and acceleration of the structure is 0. We proceed to the next time step by evaluating the force at that step and solving the structure to obtain the new values of the displacement, velocity, acceleration, and internal forces. We then start over again by advancing to the next time step. We continue this process until we reach the final time of the analysis. The final solution of the time history analysis is a complete record of the behavior of the structure at every time step, starting from 0 until the end time of the analysis. The time history analysis is a general and accurate method that can be used for any loading condition and can be used for nonlinear problems. It also gives a complete record of the behavior of the structure with time, therefore it is called time history. However, it is time-consuming and can be very slow for large problems. Model dynamic analysis is only applied to multiple degree of freedom systems. In this method, the multiple degree of freedom system is converted to a number of single degree of freedom systems according to mode shapes. The number of single degree of freedom systems is equal to the number of mode shapes. After this step, each single degree of freedom system is solved separately using a suitable method. Finally, the envelope of the solutions of the single degree of freedom systems are combined together to obtain an envelope of the solution for the multiple degree of freedom problem. The idea behind this method is to make the solution faster. For larger problems, this method becomes extremely fast when compared to time history analysis. The model analysis, however, is limited to linear analysis. The method is also approximate and only provides an envelope of the behavior. We can estimate the maximum and minimum values of the displacements and internal forces, but the method does not provide us with a complete behavior of the structure over time. Therefore, this method is suitable for design purposes where computational speed is important and where we are only interested in the maximum values of the displacements and internal forces.